Hello, I'm Xu and my student ID is CST2509050. I will be presenting Task 1, which is the implementation of a double linked list in C. In this presentation, I will explain the node structure, the function used in the program, how different edge cases are handled, and finally the program output. Before explaining the functions, let's first look at the overall workflow of the program. The program first checks whether the linked list is empty. Then it inserts three integers entered by the user. After the insertion, the linked list is displayed. Next, the user searches for values in the list. And then the program performs deletion operations and displays the updated linked list after each deletion. Finally, another search is performed to verify the final state of the linked list. This workflow demonstrates all the basic operations of a double linked list. For double linked list structures, each node contains three parts. The first part is the previous pointer, which points to the previous code. The second part is data, which stores the integer value. The third part is the next pointer, which points to the next node. Since each node stores both previous and next pointers, the list can be traversed in both forward and backward directions. This is the main difference between a single linked list and a double linked list. For 5 functions, the first function is empty. The purpose of this function is to determine whether the linked list contains any node. The function checks whether the hand pointer is equal to none. If hand pointer is none, it means the linked list is empty and unappropriative. A message is displayed. Otherwise, the program informs the user that the linked list is not empty. This function is useful because it prevents unnecessary operations on an empty linked list. The next function is insert node. This function inserts a new node at the beginning of the linked list. First, memory is dynamically allocated using malloc. Then, the user's integer is stored inside the new node. The new pointer of the new node points to the current hand. If the linked list is empty, both the hand and the tail pointers point to the new node. The third function is find node. This function searches for a specific value of the linked list. The search always starts from the hand node. A temporary pointer moves through the linked list one node at a time while comparing each node with the target value. At the same time, a position counter records the current position. If the value is found, the program displays its position. Otherwise, after reaching the end of the linked list, the program displays a message indicating that the value was not found. The most important function is delete node, because it has to handle several different situations. First, the function checks whether the linked list is empty. If it's empty, the deletion process stops immediately. Otherwise, the function searches for the node of contains the specific value. If the value doesn't exist, the program informs the user that the node cannot be found. If the node should be detected is hand node, the hand pointer is updated to point to the next node. If the deleted node is in the middle of the list, the previous node is linked directly of the next node. If the deleted node is the last node, the tail pointer is updated to the previous node. Then the memory occupied by the deleted node is released useful. This prevents memory leaks and keeps the linked list correctly and connected. Finally, display appropriate message. The last function is display list. This function prints all the nodes currently stored in the linked list. It starts from the hand node and traverses the linked list until it reaches none. During traversal, every node's value is displayed together with a loss to illustrate the list between nodes. This allows users to clearly observe the structure of linked list after every operation. Besides the basic operations, the program also handles several edge cases. When the list is empty, the program displays an appropriate message instead of performing invalid operations. The second case is a single node linked list. After deleting the only node, both the hand and the tail pointers are updated to null, indicating that the linked list has become empty. The third case is when the user searches for or attempts to delete a value that doesn't exist. Instead of crashing, the program simply displays a non-found message. Handling these edge cases makes the program more reliable and strong. For the sample output of the program, first, the program displays the linked list is empty. Second, 3 integers are inserted into the linked list. Since every new node is inserted at the beginning, the final order is the reverse of the input order. Next, the search function correctly reports whether a value exists and displays its position. During deletion, the linked list is updated after every successful deletion. If the value doesn't exist, the program displays an appropriate message without modifying the linked list. Another search is to display the final state of the linked list. Overall, the output demonstrates that all required operations of the double linked list that are working correctly. This concludes my explanation of task 1. I will now hand over to my teammate who will continue with task 2, which is the implementation of a stack using a single linked list.
Hello, I'm Xia Youran, student ID CST2509047. In this video, I will introduce the second program of Assignment 2, which is about the implementation of stack. First, I'd like to explain why a linked list is suitable for implementing a stack. Stack is a linear data structure that follows last in, first out principle. The last data added to the stack will be the first value removed. And linked list is also linear. It can achieve LIFO principle by adding the nodes to the top and remove nodes from the top. Besides, linked list can dynamically grow or shrink so that the size of stack can be adjusted as we want, and the use of memory is more efficient. Next, how the top of the stack is represented. In this program, the top of stack is represented by a node type of pointer called top. This top pointer will always point to the first node of the linked list. Then I will explain each function in this program. The first function is add, which performs push operation. It receives the address of top pointer and the value to be added. In this function, the program first uses malloc to allocate memory for a new node. If the allocation fails, the program will print memory allocation failed. And if the allocation is successful, the value will be stored in new node data, and new node next will point to the current top pointer. Finally, the top pointer will be updated and point to the new node. The second function is withdraw, which performs pop operation. It removes the top value of the stack and return it. In this function, the program first checks whether the stack is empty. If the stack is empty, which is the stack underflow situation, the program can't remove any value from it. So it prints the stack is empty, cannot withdraw, and return to the main function. If the stack is not empty, the program first stores the top value of stack into a variable called value. Then it uses a temporary pointer called temp to store the current top pointer. After that, the top pointer will point to temp next, which means the top pointer point to the next node. And finally, the old top node will be freed by using free temp. The third function is display, which shows all the value in the stack from the top to the bottom. In this function, first, it checks whether the stack is empty. If it is empty, it prints the stack is empty. If it is not empty, it creates a temporary pointer called temp and set it equal to top. Then it uses a while loop to traverse the stack. In each loop, the program prints the temp data and moves the temp to temp next. This will continue until temp is null. The fourth function is counting, which counts and displays the number of elements in stack. It starts with an integer variable I equal to 0. If the stack is empty, it prints number of items in stack is 0. And if the stack is not empty, it creates a temporary variable temp to traverse the stack. In each loop, the counter I will increase by 1. This will continue until the pointer reaches null. The next topic is how the menu and switch case control program flow. The menu is inside a do-while loop, which means it will continue to appear until the user enters option 4, which is exit. The program asks the user to enter an integer between 1 to 4. It also checks for input validation. If the input is not an integer, it will print an error message, then clear the character out of the input buffer and return to the menu. After the program receives a valid input, it will go to the switch case statement. Case 1 is add. It asks the user to enter a value, then call the add function, and then display the updated stack. Case 2 is withdraw. It first checks whether the stack is empty. If it is not empty, it calls the withdraw function and then shows the remaining stack. Case 3 is stack count. The program calls counting function to show the number of items, and then it calls display function to show the current stack. And case 4 is exit. After exit, the program will free all the dynamically allocated memory to prevent memory leak. If the input is beyond 1 to 4, which is default cases, the program will tell the user the input is invalid and prompt the user to input again. Now I will show and explain the output. This is the menu. I enter 1 to add a value to the stack. Let's say we add 10. So now there's one element in the stack, and I continue to add a value. Let's say 30. So this is the current stack. Next, I enter 3, which shows the number of items and the content of current stack. Then I enter 2 to delete a value. Now there's only 10 in the stack. And I continue to remove. We can see now the stack is empty, and the program will remind us that the stack is empty, so cannot withdraw. And if I enter, let's say 5, the program will tell us invalid input, please enter again. And last, I enter 4, which will end the program. I'll make a brief conclusion on this assignment. For task 1, we understand the implementation of linked lists in C and enhanced our programming skill regarding pointers and dynamic memory allocation. We also learned how various linked list operations, such as insertion and deletion function. The most challenging aspect was handling the different deletion scenarios, because most of them require specific pointer updates. And we overcome this challenge by sketching the linked list structure, tracking changes to previous and next pointers, and testing the program with various inputs, including edge cases like empty lists and single node lists. And for task 2, we learned how a stack can be implemented using a linked list in C programming. One of the biggest challenges we faced was understanding pointer operations, especially updating the top pointer and passing it to functions correctly. And to solve these problems, we carefully traced the program step by step, drew diagrams of the linked list, and tested the program with different inputs. So this is all for our presentation. Thank you for listening.